Okay, in this presentation, I'm going to talk about some important results in learning theory. And especially, we are going to discuss the concepts of bias versus variance. And we are going to study how these two concepts are related when we talk about a class of hypotheses which contains a finite number of hypotheses, and also in the case where we have an infinite number of hypotheses. We will also talk about the concept of empirical risk minimization. So, talking about learning theory is a research field devoted to study and designing machine learning algorithms. But the emphasis here is in formal analysis. So we're talking about rigorous mathematical analysis of different parts of the learning algorithms. We usually use probability theory, statistics, optimization, some concepts in information theory like entropy or geometry, for example. So the emphasis, as I said, is on mathematical analysis. So the idea is to prove theorems about the algorithms. And in the end, the search is for efficient machine learning algorithms. Most of the results that we study in machine learning theory lead so far to not very practical algorithms, because in general machine learning is a very complex problem, a difficult problem. But the main goal behind learning this theory is to be able to design new algorithms that will be efficiently implemented. So let's talk first about the trade-off between bias and variance. If you recall the linear regression problem, the linear regression algorithm, we wanted to fit a curve given a set of points, and we were looking for the best degree of a polynomial that could fit the points. So in this plot here, we see three curves. Okay, and to the left, we see the plot of a straight line, which will correspond to the first model here, polynomial of degree 1. And to the right, we see a polynomial of degree 5. And as you can see here, the polynomial of degree 5 manages to turn perfectly and passes by exactly on every single point. So this fifth order polynomial is not a good model, actually, because it will not generalize well. So the idea of generalization is like the main goal behind machine learning. The idea is that you will learn some model that will be useful for future points. If you want to classify new points, or if you want to predict the output for a given input x variable. So the generalization error of a hypothesis h of x with parameters theta is its expected error on examples not necessarily in the training set. Okay, so in the end, what we want to minimize is this generalization error. In these models that we have seen here, the leftmost, this model here, and this here to the right have larger generalization errors, or we expect to have larger generalization error than this model in the center. So both models have problems. Let's say they are not optimal, but the problems are different. So this model here to the left has an underfitting problem. So the model cannot extract the patterns or the structure of the data. And this is because this simply a straight line and it cannot turn at all. So we will see that this problem is called a strong bias. It's very not very flexible, let's say. And this problem here is the overfitting problem. And this is in the other extreme of underfitting. In this case, we have too many parameters, and the model basically memorized the points, and this will create a problem with a large generalization error. So we're going to talk about these two kind of problems. One is caused by the bias and the other is by the variance. First, we will talk about this in a very intuitive way, and later we will talk more formally. So if the relationship between x and y is not linear, then even if we were feeding a linear model to a very large amount of training data, so even if you have too many examples, the linear model would still fail to accurately capture the structure in the data. So even if we increase the number of examples, since our model cannot turn, it is very fixed as a straight line, then we cannot improve the generalization. We cannot reduce the generalization error. So informally, when this is the case, we say that this has a large bias. So we define the bias of a model to be the expected generalization error, even if we were to feed it to a very large training set. Okay. For the problem above, the linear model suffers from a large bias and may underfit the data. So it may fail to capture the structure that is in the data. On the other hand, the variance of a model is a second component of the generalization error. When, for example, fitting a fifth-order polynomial, there is a risk that we're feeding patterns in the data that happen to be present in our small training set, but that do not reflect the wider pattern of the relationship between x and y. So if we have a model with too many parameters, like in this case, it could happen that the model will learn every single point, and that means that any slight change in the points, in the position of the points, will cause a big change in the curve. So perhaps in the training set we have like a different value for one point, like for example this. If the point were up here, our model will make changes to cope with this point, and maybe the final model would look something like this. So even small changes in the dataset will can make large changes in the model. And the problem is when we have maybe one or many points in our data set that are maybe they are noisy, or maybe they are simply not very representative of the points that we want to learn. And our model, if it has a large variance, could be very sensitive to these noisy points or unrepresentative points. So this is would be a case of large variance, and this is the second cause of large generalization error. So there is often a trade-off between bias and variance, like in the problem of linear regression. We need to increase the degree of the polynomial in order to reduce the error, but we should be very careful in not increasing the degree so much that we will end up with large generalization error because of large variance. So if our model is too simple, like just a straight line, we will have a large bias. So our model is very biased. We are saying that, okay, maybe our data behaves like in a straight line. So we are imposing a large bias. And in that situation, we will have a small variance. Or we can have the other way around, a model that is too complex. So it has many parameters. This model suffers from large variance and small bias. So summarizing this in a table, we see that if our model is very simple for our dataset, we will have few parameters. The bias is going to be large and the variance is small. And if the model is complex, we will have many parameters. The bias is going to be small and the variance is going to be large. In our example, fitting a quadratic function does better than either the extremes, a first degree or a fifth order polynomial. Now, can we make formal this trade-off between bias and variance? Is it possible to make this or analyze this mathematically? Another question would be, can we relate the error in the training set to the generalization error? So remember, the error that we can calculate is the error with the data that we have available. So this is the error in the training set. And what we are asking here is there a relationship between this error in the training set with the error of generalization? So this is the error with new points that we don't have yet. Is there a way to relate these two kinds of errors? And a third question that we can ask here is, are there conditions under which we can actually prove that learning algorithms will work well? So this is a question regarding the performance of our algorithms. And the question is, are there some conditions or constraints or assumptions that we can make to prove how good our algorithms are going to work? So we are going to review some of the most important results, theoretical results, to try to answer these three questions.